start, okay? So please.
All right, sounds good. Do you see my slides well? And the cursor?
Yes, it's all working.
Okay, very good. Hi everyone. It's a pleasure to be here. I'd like to start by thanking the organizers for giving me the opportunity to present my work here. I've never attended the Strings Online Lisbon workshop, but it seems from the program that it's going to be a great conference. And my talk today will be focused on questions related to the reflection and transmission of energy from conformal interfaces. I'll explain what's so interesting about that in a moment. And I'll try to convince you that there's benefit to try and answer these questions from the perspective of gravitational holography. Now, this work is based on several collaborations and work in progress with the people whose photos you see on the slide. And let me just mention that the two photos with the red note are Stefano Baiguera over here and Sebastian Weber, and they are both applying for postdocs this season, and they're both awesome. So I'll just say that. In case you're looking for people. So here's the outline of my talk. I'm going to start with an overview of conformal interfaces. I will then describe in detail the question I'm asking about energy transport, and I will then also explain what's special about 2 dimensions. For this question, I'll then introduce different holographic setups where this question can be studied. First, there will be a model involving a thin brain in 2 dimensions and then in general dimensions. And then I will consider a slightly more realistic model with a smooth domain wall solution in the bulk. Janus is an example. I'll tell you the outcome for the energy transmission in each one of those models. And of course, at the end, I will summarize and list some interesting future directions. Feel free to stop me at any time. I'm very happy for questions. The talk is divided in such a way that the last part, the one about a smooth domain wall, is not absolutely crucial for the point of the talk. So it's not a problem if I don't get to it. So please stop me at any moment. Okay, so let me start with a brief overview of conformal interfaces. So first things first, what are interfaces in general? Interfaces are codimension 1, extended objects which split a system into 2 parts. So here in the picture you see 2 examples of a conformal interface drawn just in space for now without time. The left example is in 1 + 1 dimensions. Again, I only draw space. And in this case, an interface is just an impurity in a chain. In 3 + 1 dimension, there are simply 2-dimensional surfaces that at a given time that split the system into 2. And as usual in physics, when there's more symmetry, one can say more about the system. And a particularly symmetric kind of interfaces are conformal interfaces, which separate 2 critical systems and preserve the largest possible subgroup of the conformal symmetry. So that's going to be in Euclidean an SOD(1) subgroup of the conformal symmetry of the entire space, SOD + 1, 1. Specifically in 2D, the symmetry is much larger. Conformal theories usually preserve 2 copies of the Virasoro, and when we add an interface, or say an impurity in this case, it breaks an entire copy of the Virasoro, but keeps still infinitely many symmetries. There is still 1 copy of the Virasoro which is preserved. So you can imagine that we can say quite a lot about these systems, even in the presence of an interface. So what are conformal interfaces good for? Let me give you some motivation. Conformal interfaces are good because they appear in many physical systems. To begin with, they provide a good description of interesting systems in condensed matter that includes junctions of quantum wires and line or surface defects in the critical 2 or 3D Ising models. They appear almost everywhere in holography. There are various ways to model them, including dynamical branes in ADS, which have in recent years played important role in the context of double holographic modeling of black hole evaporation. And they appear in supergravity solutions, for instance, for Janus. They provide a useful playground for computations in quantum informations. So this, for example, in islands of black hole evaporation, where they serve as end-of-the-world branes on which the black hole lives. They are important also in the context of RG flows. When we have RG flows, there are new anomalies in the system, and these anomalies can be monotonic. That helps constrain systems with interfaces. So that's interesting as well. And there are many, many more places in physics where we encounter interfaces. They're kind of everywhere. At the end of the day, the systems we study in physics usually have some impurities or they have some defects. So that's kind of natural setup to think about. All right, so now that you are hopefully convinced that conformal interfaces appear everywhere, let me tell you a bit how we describe them. Let's first look at the drawing over here. Let me get my cursor back. So this is a drawing of a wall separating a right CFT from a left CFT along a constant, let's say, x equals to 0 surface. Typically, I will have one coordinate which is perpendicular to the interface. And in addition, inside the interface will be time-like, so time will run inside it. And there could be, if I'm in more than 2 dimensions, additional space coordinates. Of course, when I add an object like that in my theory, that breaks some of the conformal symmetry. The simplest thing you can think about is that, say, the trivial part of translations, which appear in more than just the conformal group. But of course, if I have an interface, then translations perpendicular to the interface change the system. They move the interface. And that usually gives rise to energy conservation. So when I have an interface, energy conservation of the stress tensor is violated in certain direction, exactly those directions involving translations in the direction of the interface. So that would give a non-vanishing contribution to the divergence of the stress tensor when I cross the interface. This divergence is related to an operator which is kind of commonly used in this literature on interfaces and defects. It's called the displacement operator. It's an operator that when we add into correlation functions, it essentially tells us what would be the correlation function with the displaced interface or defect. But nevertheless, as you see, some conservations still hold. We still have translations in the time direction or in the directions which here in the drawing I denoted yi, which means that we do have some conservation, and in particular, this leads to matching conditions. So components of the stress tensor which are mixed involving the perpendicular direction and an additional direction are going to be continuous across the interface. Many things that we're used to in CFTs get slightly changed. So for example, we're used to primary operators having one-point functions which are vanishing. Now, in the presence of an interface, it's not necessarily the case. They are fixed in terms of an unknown coefficient, but they can have a VEV, even in the vacuum. There's a lot of machinery around these types of systems. The OPE has been developed as well. And if you want to know more, there's this nice review by the people on the right bottom of the slide. All right. So let's now specifically focus on 2 dimensions and tell you what's special about 2 dimensions. So when we talk about interfaces in 2 dimensions, they typically break some of the symmetry, but not too much, as we said. In the 2-dimensional case, these are just at a given time slice, they are impurities. So now with the time, they are kind of a line running along the configuration. And they preserve those Virasoro generators that don't displace the interface. So it's one linear combination infinitely many linear combinations of the original Virasoro generators of the conformal field theory. And here again, just like previously, the remaining energy conservation implies that these mixed components Txt of the stress tensor are continuous across the interface. This can also be expressed in terms of the holomorphic and anti-holomorphic part of the stress tensor. All right. Some other interesting things about conformal interfaces in 2 dimensions have to do with correlation functions of the stress tensor. So in usual CFTs, all the correlation functions of the stress tensor, holomorphic or anti-holomorphic, are completely fixed by the very large conformal symmetry. In the case of theories with an interface, only 2 and 3 point functions of the stress tensor are fixed. And when I say fixed, I mean that they depend on some unknown coefficients rather than unknown functions. So of course, they are quite similar to what you could expect. If I have a left and a right CFT, I'm going to have the left and a right holomorphic stress tensor, for example, where correlations of the left stress tensor with itself are just going to be dictated as in usual CFT in terms of the left central charge. Correlation functions of the right stress tensor are going to be dictated in terms of the right central charge. But now we have also new types of correlation functions which we didn't have before. For instance, mixed correlation functions of stress tensors on the left and right, which are going to be fixed in terms of a new coefficient, which I'm going to call C left right. So pay attention to this guy over here, C left right, because it's going to be the star of the play. It's going to play a very important role when I ask questions about the reflection and transmission of energy from this type of interfaces. Yeah, as I said, 3-point functions are also fixed, but 4-point functions are not. All right, so now that you have a bit of background related to conformal interfaces, let me describe what exactly is the experiment that I'm thinking about. And at the same time, I'm going to tell you how to measure this C left-right, essentially. So imagine the following setup. Imagine a scattering experiment when someone organizes some fancy lump of energy and sends it in the direction of the interface. This lump of energy splits. Some of it is reflected and some of it is transmitted. And the question that I want to ask is, what is the ratio of transmitted energy over the incident energy? So I'm going to define 2 quantities, T, which is the transmitted, the portion of energy which is transmitted, and R, which is the portion of energy which is reflected in this type of scattering experiment. Right. In principle, when the 2 CFTs are different, this experiment can behave differently if I'm hitting the interface from the right and the left. So I will append a subscript to this tau to say whether my experiment took place, whether I hit an incident wave packet from the left or from the right in my experiment. Yeah. Now, before I move on, I want to make the comment that scattering, I mean, I describe it in very like kind of a simplistic way, because scattering experiments in CFT are very subtle. Since we have this kind of zoom in, zoom out symmetry, we lack asymptotic states. But Hoffman and Maldacena in their conformal collider physics paper defined some sort of scattering experiment in CFT, and somehow underlying everything that I'm telling you today is their definition of a scattering experiment in CFT. It roughly relies on defining the amount of energy in terms of ANEC operators at the infinity of Minkowski space. So for those that are worried about this point. All right, so let's focus on the 2-dimensional case. It's very special since, as I said earlier, it has much more symmetry. And this enlarged symmetry has an interesting consequence, which is universality in this scattering experiment. So essentially what I mean by this is that the portion of scattered and reflected energy turns out to be completely independent of the details of the incoming excitation. So it depends on the theory. But within a given theory, it doesn't depend on what you send. You can organize whatever operators that you want in whatever form of wave packet, and always the percentage of energy which is transmitted and reflected will be the same. This property was proven rigorously in 2019 by Meneri, Penedones, and Rousset, and that's the paper quoted on the bottom of the slide. And what they showed essentially was that the outcome of the reflection and transmission experiment is completely dictated by this one coefficient C left right in the 2-point function of the left and right stress tensor. So it's if I do my experiment sending a wave packet from the left, the portion of transmitted energy will be C left right over C left. And if it is from the right, then it will be C left right over C right. The reflection, of course, is 1 minus the transmission. At least that's what we would hope. And they also showed, that's a fancy way of saying it, but that the ENEC essentially tells you that we would like both reflection and transmission from either side to be bounded between 0 and 1. And that means that if I have two different theories, one with a larger central charge and one with a smaller central charge, then I cannot fully transmit energy. So I cannot have transmission equal to 1 from a theory with a larger central charge to one with lower central charge. This just comes by crossing the restrictions coming from this T and R being between 0 and 1 for experiments from both sides. And that has a kind of an intuitive explanation because many times we think of these central charges as counting the degrees of freedom. And so what this essentially means is that when we hit a perturbation from a region with higher number of degrees of freedom to one with lower number of degrees of freedom, there are not enough degrees of freedom to carry the energy away. So essentially it means that if the right central charge is lower, then transmission from the left cannot reach 1, cannot be perfect. At most, it can reach the ratio of the central charges. Okay, good. There's this comment here also that is interesting, is that there are other bounds also relating experiments with energy to experiments with entropy, or trying to claim to relate to experiments with entropy transmission across such interfaces. I'll have some comments about that at the very end. All right, so remember these bounds. They will be back when we study holographic setups. We will be able to recover some of them. Yeah, I have 2 slides here about how that claim is proven. And well, basically what these authors did is they used CFT2 techniques. They took an operator and they bounded it in a region which is relatively small compared to the distance from the interface by some enveloping functions. And then they defined the reflection and transmission in terms of these AMAC operators. So essentially integrals of the stress tensor on null rays very far from the interface. In this way, the question of transmission and reflection just became a question about 3-point functions of these NEC operators and 2 operators creating the perturbation, which they could solve with 2D CFT technique. Of course, that's very limited to 2 dimensions. We have much more tools in 2 dimensions to compute this type of correlation functions. At the moment, we don't know anything about dimensions greater than 2. So we don't even know what to expect. We don't know if to expect universality. And I will try to tell you today that we can use holography to gain some intuition to this question. All right, so in the next part of my talk, as I said, I'll try to convince you that holography can help us with looking at this problem. So what I will do now is to reframe the same energy scattering experiment from a holographic gravitational perspective. for relatively simple holographic models, which are very commonly used in different contexts. So this will include two models. The first one is a thin brain in a thin ADSD brain connecting two patches of ADSD plus one. That's one way to model interfaces in holography. Very simplistically, it's like kind of a bottom-up construction. And using this model, I will conduct the experiment in 2 dimensions. I will confirm that the results are universal to some extent, and I will be able to extract the transmission coefficient or the C left right equivalently. In D greater than 2, a priori, we don't know what to expect, but I'll show you that we can study it in holography, and we have some hints of universality in specific cases. And then if I have time, I'm going to talk about smooth domain walls, which are a slightly more realistic scenario where we have a continuous geometry with the dilaton. These are geometries that can be obtained by a reduction of certain supergravity systems. So they are much kind of more, we understand them better. We understand the field theory dual better. Okay, so
Shira, may I ask a
yeah,
question here? Is there
absolutely.
a supersymmetric version of this defect construction?
So yes, the Janus geometries have supersymmetric versions. We haven't studied them. We did like very minimalistic setup, at least when we were looking at the continuous geometry, which is just metric plus dilaton. But I think there's still much more to try and do there. I think Karch had a paper where he was trying to say something more very recently. But yeah, I will show you that, well, yeah, anything that it's already quite hard to look at very minimalistic smooth domain walls, and we didn't actually solve it. We did it with a very nice trick, but yeah, we needed a trick to solve it. It was not non-trivial even in this like very simple.
Yeah, I was actually thinking more about the CFT side and about the supersymmetry of the defect. Is there
Oh,
something
I
like
see, I
that?
see, I see. You mean if it has been classified when the theory to begin with is super conformal theory or just
Yeah.
symmetric? Yes, I know that Nadav Drucker has some works on that, on classifying what an interface can at most preserve out of the supersymmetry. Yeah,
Okay.
I don't know if it's because yeah, these classifications, they vary depending on codimension. The case that is most famous is, so it's actually not interfaces, so not codimension 1, but codimension 2. For example, you find them in supersymmetric Renyi entropies. This you definitely know that they can preserve some of the SUSY. But I think Nadav had like a classification, what can different codimensions and different dimensions of the space-time, what can they preserve from different original supersymmetries. I don't know how broad it is. I don't remember.
Okay, thanks.
All right, good. Okay, so I just wanted to say why study the scattering experiment in holography. So one reason I already hinted, which is to get a window to interface CFT scattering in higher dimension, for which we don't know what to do with CFT techniques. Another reason is that we would like to understand better these widely used holographic models. So the thin brains are quite an extreme example where you can see them in many works. For instance, they serve in these end-of-the-world brains for black hole evaporation and so on, but the field theory is very poorly understood. In particular, correlation functions are only computed in some limits or some very specific versions of the model, if at all. Even a well-defined Pfefferman-Graham procedure is not completely well-defined. So there are many problems. Yeah, and for example, two-point functions of stress tensors definitely have not been computed there. So by doing this scattering experiment, we get a probe to certain correlation functions, essentially even in 2D. Another reason would be to study the properties of the transmission and reflection at strong coupling or large central charge. So even in 2D, where we know that the result should be universal, we still don't know what's the value of the transmission coefficient, and it's nice to see if it has any special properties at strong coupling or large central charge. Okay, so with all these goals in mind, let's start with the first holographic model, which is the thin brain model. And so that's a very, very simplistic bottom-up toy model, which we use in holography to describe interfaces. And it's constructed in the following way. So the idea is the following. The gravitational solution has two patches of ADS, one whose boundary is the left CFT, and another one whose boundary is the right CFT. And these two patches are glued with a constant tension brain connecting them. I lost my cursor. Apparently, okay. Right. So the two patches are glued along a constant tension brain. So in more explicit terms, the idea is to look for a solution of Einstein equations that has on a certain region of space-time an action which depends on a left cosmological constant or left ADS radius. I'll call it L left. On another one on the right, potentially other one, and depends on a brain tension sigma, which is a simple term integrating the induced metric on the brain. Now, in this case, of course, a solution to Einstein equation would be just, ADS on the left, ADS on the right. And the only thing which remains to be fixed is the location of the brain. So that's done by solving Israel matching conditions. That's a standard thing. Israel matching conditions tell us that when we have a constant tension brain, the patches across it have to be matched such that the induced metric is continuous and the extrinsic curvature jumps by an amount proportional to the tension. So in effect, what happens when we solve these equations is that we get not half ADS and half ADS, but slightly more than half ADS glued to slightly more than half ADS, where how much slightly more depends on these angles theta left and theta right, for which the Israel matching conditions solve. As usual in holography, the two cosmological constants are related to the two central charges of the two sides. All right. And it turns out that the equations of motion, in this case, have stable solutions with a thin ADS-D brain, as long as the tension is between certain bounds, depending on the radii of curvature of the two sides. The lower bound comes from essentially stability of the action, the action being extremized by the solution with the brain. And the upper bound comes from a limit in which the brain geometry becomes de Sitter. And the angles can be fixed by the matching condition, as I said. Essentially, you have to solve a set of equations. If you know the left and right curvature radii and the tension, you can solve for these angles and understand exactly how much more than half ADS you have on each side of this configuration. All right. We can also construct solutions with several thin brains anchored on the same interface. That's one comment. Another comment is that the thin brain model, I already said it once or twice, gathered a lot of interest, especially in double holographic models of black hole evaporation, and that despite being common, they are very poorly understood, especially in terms of their correlation functions. Another comment has to do with what has been computed in these models. So it's true that correlation functions have not been computed too much, but the thing that people typically compute in these models is boundary or interface entropy. So essentially, how much more entanglement entropy do we have in an interval surrounding the interface compared to a case where there is no interface. It turns out that this interface of boundary entropy is fixed by the tension by certain expressions that one can find in the literature. Of course, tension is the only new parameter essentially in this theory, so it's not very surprising. Yeah. All right. So with this at hand, it's time to go back to the scattering experiment. So let me start with 2 dimensions, which is the simplest case. What we would like to do is find the transport coefficient for a scattering experiment in holography. Of course, 2D is the simplest case, also because we kind of know what to expect from the field theory point of view. We have this proof of universality. So we would like to perform a scattering experiment for a small but general excitation. And the idea is that every excitation can be decomposed in plane waves. And so we can just, if the excitation is small enough, work in a way which is linearized in the perturbation in such a way that every plane wave mode can be treated separately. So that's what I'm going to do. And okay, then superpose them to give whatever wave packet we want. So that means that we are going to try and look for a bulk solution which is dual to a stress tensor, which has a wave of amplitude, relative amplitude 1 coming from the left, relative amplitude R left for a reflected wave, which goes away from the interface on the left. And on the right-hand side, we look for a solution that has a relative amplitude of the transmission coefficient T left and goes away from the interface. Now there is this characteristic frequency omega that then we will superpose to give whatever we want. Now the bulk solution, and that's something very special to 3-dimensional bulks or 2-dimensional boundaries, is completely fixed. So it's truncated in the Pfefferman-Graham expansion, and knowing the stress tensor, we can just build it entirely. It has a second correction to the metric that depends on the stress tensor, and a 4th order correction to the metric that depends on the stress tensor square, and that's where it chops. So we really have, knowing the stress tensor, the exact solution on the left of the brane and on the right of the brane. And of course, that leaves us to find the position of the brane. So you remember that without a metric perturbation, the 2 sides were matched along a brane with angles theta left and theta right. And essentially what the perturbation now does is that it modifies the shape of the brane. It makes it kind of wiggle. And these wiggles we have to solve from because they will be the one fixing constraints on our incoming and outgoing perturbation. They will give us constraints on these relative amplitudes. And so the method is the following. So we will impose Israel matching conditions and boundary conditions in the sense that we don't want we want a straight interface when we go all the way to the boundary. So the brane still has to be anchored on a straight line. And those 2 things together give the constraint that reflection plus transmission equal 1. That at least we could have hoped if the experiment makes sense. Another kind of standard conditions that we have to impose that is very commonly encountered in correlation functions in ADS-CFT is some no outgoing wave condition in the infrared. That's a condition that one usually imposes when computing a retarded correlation function, which is appropriate for this type of experiment. And once imposing this no outgoing wave, so no waves are crawling up the brane towards the boundary, we get a result, we get a constraint for the transmission, and it's completely fixed in terms of the left and right central charges and the brane tension. So that's in 2 dimensions. I'll show you in a second how that changes in higher dimensions. But let's first observe a few properties of this solution. The first property is that this transmission is monotonically decreasing with the tension. That's kind of a sensible thing. If the brane is more rigid or more tense, we expect that less energy can pass and more will be reflected. We can look at limits. So for instance, when we have 0 brane tension, an equal number of degrees of freedom on the right and left, In this case, the transmission gives 1, which is really what we would expect for essentially a situation without a brain. There's some degree of universality, maybe not as broad as was proven in CFT, but at least we see that the result doesn't depend on the frequency. So really we can superpose whatever kind of wave packet we want. In this case, they are just metric perturbations, so they are constructed by stress tensor insertions. They are not the most general operator a CFT can offer, but no matter how we superpose them, we're going to get the same portion of energy being reflected and transmitted. And since this holographic model only has one parameter, which is the tension, in this specific case, the transmission and the boundary entropy, which I mentioned before, are both fixed in terms of this one parameter. So it kind of looks like they are related. This, I will tell you, it's not a generic thing, but you could have wondered if it's generic for, say, strongly coupled theories. All right, very good. Some more consistency checks. As I said, to have a stable solution with a thin brain in the bulk, there is some range of tensions which are allowed. And if I check what this range of tensions which are allowed impose for the transmission, what I find is that the transmission is indeed bounded by this. I don't know if you remember, but the minimum of 1 and the ratio of the central charges. So you remember this was the statement of not being able to fully transmit from higher to lower central charges. The lower bound is more restrictive than what happens with the ANEC or what happens with the field theory result. So it's consistent with the ANEC, but the lower bound is stronger. And in particular, this stronger lower bound says that we can only have total reflection or zero transmission if the ratio of degrees of freedom goes to 0. So we can have full reflection of only if we completely, in this very simplistic model, only if we completely turn off the degrees of freedom of one side out of the two. That's again not generic, but you could have wondered, is this generic for strongly coupled theories? All right. These two questions, or whether these funny features of scattering in 2 dimensions with a thin brain were answered by Baig and Karch. They made a slightly more general model where they included 2 brains. The transmission in that case was sensitive to the sum of the tension, and in this way they were able, they were able to show that the transmission and log G are generally independent, and that the lower bound, so full reflection, can be realized without completely turning off one side in a slightly more general model. So this brings me, wait, let me pause for some questions before I go to the higher dimensional case. All right, so this brings me to the second part of my talk, which is what, the next part of my talk, which is the idea of looking at higher dimensions with essentially the same model. The higher dimensional setup is richer. So one of the obvious things is that now in 1+1 dimensions, this interface was just an impurity. So there were no directions I could approach. It's just one direction. But in higher dimensions, the excitation can hit the interface at an angle. So that's already much richer setup. The other thing is that we have much less symmetry. So the conformal group is now finite dimensional, so it's less constrained. And we don't have, therefore, a CFT result, so we don't know what to expect. In holography, the solutions don't truncate at a finite order in the Pfefferman-Graham expansion, which adds some computational difficulty to solving this in holography. So what we did was to start with the simplest thing you could think of, and you will see that that's already very non-trivial, which is to look at head-on collisions in specific dimensions. Head-on meaning they hit directly on the interface without an incidence angle in 4-dimensional bulk, 3-dimensional CFT, or 5-dimensional bulk and 4-dimensional CFT. And it turns out that even these head-on collisions are quite non-trivial. They require quite a bit of new machinery. But the idea is roughly the same. We need to be looking at perturbations of the thin brain metric, so some perturbations, which can be decomposed in plane waves, so e to the I omega t, and whatever spatial dependence, where when I talk about head-on, I mean no dependence on these yi's, additional spatial coordinates along the brain. And what we would like to do is try and build solution corresponding to an initial desired excitation by imposing some boundary conditions on the metrics on the left and right side, the way we usually do in holography. It turns out that excitations for expectation values of the stress tensor decouple to 3 different sectors that can be treated separately. There's a vector sector and a transverse traceless. I'm going to focus on a sector which involves the transverse traceless part of the T and X part of the stress tensor. And then essentially we have to solve for the bulk with these boundary conditions. And once the bulk is solved, we need to solve for the brain fluctuations using Israel matching and impose no outgoing wave condition in hope to find the transmission coefficient in the higher dimensional case for head-on collisions, at least to begin with. So what is special now in higher dimension? It turns out that plane wave stress tensor modes, like we had in 2 dimensions, e to the I omega t minus I omega x, are no longer solutions of the gravity equation. And you can think of a very simple example where something similar happens, which is if you try to solve a Laplacian for a scalar field, which has an e to the I omega t dependence on slices of ADS2, this scalar field is going to have solutions which are plane waves. But if you try to do the same for slices which are ADS3, the solutions are going to be Bessel functions. So instead of plane waves, instead of getting things like e to the I omega t minus ikx, we get contributions which are essentially in modes of Bessel functions with Bessel coefficients which when n is large, take essentially a linear form. And the reason why that's a problem and why we got stuck on that for quite a while is that all these Bessel functions decay when you go away from the interface. So essentially you get something that oscillates, but also decays. And so naively, if you look at all these modes of the solution, it looks like you can just not have anything in this geometry propagating because everything turns off when you go away from the interface. But it turns out that you can organize series of these Bessel functions, infinite series, only infinite series, which do sum to plane waves. And in this way, you can start to construct everything you want. So that puzzled us for a while, but we were able to formulate a rigorous theorem about how to sum these infinitely many Bessel functions. And guess what? The result is really simple. So the result is really similar to 2 dimensions. After going through all the steps, we get a transmission coefficient, which is roughly the same expression we had in 2 dimensions with only this factor of d minus 1 in the denominator. And that's lucky because the constraints on the brain tension coming from stability also had a d minus 1. And that means that if we look at the allowed ranges of the transmission coefficient, we again reproduce exactly the upper bound from the annex. So we again don't have full transmission from a lower number of degrees of freedom to a higher number of degrees of freedom to a lower number of degrees of freedom. So that's rather interesting. It's all completely consistent with the ANEC bounds. There's again this basic test of universality, which, sorry, that's a typo, but we see that there is a frequency independence. We tested it in 4 and 5 dimension. I'm not sure if that's very surprising, but it required quite a lot of work already. So what about angles? So angles are harder. We didn't solve them yet, but we're working on that. And they involve additional directions in the PDEs, so they become quite a messy goo of equations, but it's possible that we will be able to solve them in an expansion in small angles, and hopefully next time we talk, I'll be able to comment on that. All right, I don't have a lot of time, so I'm just gonna give you a glance at the more realistic models. So the thin brane models has some problems or shortcomings. One is that it's discontinuous. It has like kind of delta function localized energy. Another problem is that it's completely bottom up. We don't know what's the field theory dual. And so to try and address these problems, we also looked at smooth gravity solutions, kind of top down to some extent, or at least they can be obtained from a reduction of well understood supergravity model. So these are these smooth ADS domain walls. I'm just going to show you how they look. So they are solutions to gravity plus a dilaton with a certain potential, which can be foliated in ADS-D slices, roughly speaking, with a certain profile for the dilaton. And we wanted to look for this, so since these models are much better understood, we wanted to do, again, the same scattering experiment in this configuration, which turns out to be extremely non-trivial from the mathematical point of view. But we found a trick that you can understand without looking too much into the mathematics. The idea was to look at these geometries, which are foliated in ADS-D slices, as a collection of tiny wedges of ADS space, which are glued with constant tension branes, again, everything infinitesimal. So we were able to build a friend geometry to these Janus or smooth domain walls, which essentially consist of infinitesimal wedges of ADS space glued with branes. And we already knew from the earlier works that the transmission is additive in the tensions of the branes. So once we were able to reinterpret this geometry as many, many thin branes, it's just the sum of the tensions of these branes that gave us the answer for the transmission. So we call this I'm going to skip a few slides, but we call this like a pizza slice kind of trick. So really reinterpreting this geometry as many, many thin slices and use additivity. So essentially, at the end of the day, the transmission is given by the sum of the tensions, where, sorry, I'm just going to show the final result, where all the infinitesimal tensions are just related to the variation of the dilaton. So that has to be integrated across the geometry. That also passes many nice tests. So, okay, sorry. Little bit hesitant. Yeah, sorry. Maybe I can show one small example for those geometries. Yeah, so that's an example of a geometry of this kind. It's called Janus. It's essentially a specific example of this geometry. The idea is that we take the bulk and we foliate it in constant Y slices, where each slice has the geometry of ADS-D. In this case, it's a 3-dimensional Janus, so each slice has a geometry of ADS2 with the bulk coordinate Z running down the slices. And y is kind of an angular coordinate that goes between the slices. As I said, there is a metric warp. So there is a metric warp factor that depends on this y and the parameter b. So it's a whole family of geometries, and a dilaton that also depends again on this parameter b, where the limit of b equals 0 is empty ADS, and b goes to 1 is essentially a limit in which the geometry breaks down, becomes like infinitely big in some directions. Yeah. So then I wanted to show you this plot. So by using this trick, we can find just a second. Yeah, we can find the reflection for these geometries in terms of the parameter b, and we see that in the limit of empty ADS, there is full transmission, and when b goes to 1, the geometry kind of explodes, the transmission goes to 0, and we have some explicit expressions for that. All right. This also satisfies Anek bounds, all the bounds that we expect. It gets exactly from 0 transmission to the maximum, which depends on the ratio of central charges, and satisfies many consistency checks. All right, so that's basically it. Let me summarize and tell you what are some interesting future directions. So the energy reflection and transmission are universal in two-dimensional conformal interfaces. We computed them in 2 holographic models, the thin brane, which is the thin brane in 2 and in higher dimensions, and some smooth domain walls. In the thin brane model, the head-on transmission is fixed by the tension, just like the boundary entropy, and bounds on Anek are satisfied, but we can't achieve a complete reflection. In general, as long as we have more than one brane, or if we look at Janus, the boundary entropy and the energy transmission will differ, and full reflection can be achieved. In higher dimensions, we don't have CFT results, but holography seemed to indicate some type of universality, at least for head-on collisions. And in smooth geometries, we saw a nice discretization trick, which provides a simpler method than direct computation. And so there are many questions that are left unanswered at this point. The first one has to do with angular dependence of higher dimensions and the other sectors which I mentioned. So what happens when we hit the interface at an angle? Can we do so universality is broader than just checking independence on the frequency. It's essentially independence of whatever the operator that created the perturbation is. And so to really test universality in full glory in holography, we would have to look at configurations with other matter fields. So we would like to do that as well. Of course, there are obvious follow-up questions, such as what's the holographic transport of an electric charge, or what's the transport in thermal states? And one maybe surprising aspect of this study is that the smooth domain wall geometries, when they are weak rotated, they become cosmological setups. They become FLRW. So the same questions about reflection and transmission from interface, once weak rotated, become questions about the production of gravity waves in quenches in cosmology. So that's also an interesting application that is worth exploring. And there is also another question which is kind of interesting in the context of the relation of these thin brane models to black holes, which is there any relation between energy and information transfer? So when we hit the interface, also information will be transferred in the sense that the division of entanglement between different parts of the system will change. And can we ask of course, with the eye towards black hole evaporation, can we ask when we cross an interface, for instance, an interface between a black hole and a bath, but even just like a conformal interface, is there a relation between the amount of energy and the amount of information which is transferred in an experiment like that? Okay, so yeah, that's it more or less. There's lots to explore, and I'm happy for questions.
Okay, well, thanks very much for this very nice talk, Shira. Thanks. Are there any questions?